All right, what's our first question? Let's center this. Right. I kind of, you might say that this is, so this question, you remember, is the one, give me 3 languages, since that one is contained in the other, contained in the other, and the outer 2 are regular and the inner one's not regular. And the reason I like this question is because people are often saying, well, right, so here, let's give the answer first. The answer is, let L1 just be the set that contains no strings. So it's the language where you just say no, right? It's definitely regular because it's, right, and here, let L3 be the language that contains everything. It's the language where you just say yes, and both of those are regular. But here's the language of strings that are 0 ins followed by, in zeros followed by in ones. It's not regular, right? And this L2 is definitely a subset of L3, and L1 is definitely a subset of L2. So did people get a reasonable answer to this?
Yes, sir. We just used A and B's instead of 0 and 1. I guess that's okay.
Yeah, same difference. But you got the exact same answers.
Yes.
Wow, well, there you go. The reason I like it is people often say, well, I can compute the answer for this string, right? But you have to be able to say yes to the yes instances and no to the no instances. And so anyway, any questions about that one? What about these 2 strings? And the answer is that they represent the exact same set, right? So what's this? This is, you have the character R or the character S, and then this is any finite string of R's and S's, right? All finite strings of R's and S's. And what's this? Well, we got to see how this is the same. And it's all about parsing it. So you take any string of S's and R's, and after each S, draw a line, right? Cut it after each S. And then let's look at each piece that's cut. Each piece will have some number of SRs followed by an S, right? Well, since we cut it after the S, it'll definitely end in an S, right? And it won't contain any other S's, right? Because we're cutting it after each S, right? And the number of R's could be 0, right? If it was SSS, then when you cut it, each one would just be S. So they would have 0 R's, but they could have any number of R's followed by an S, right? And then you repeat those blocks as many times as you want, right? Any number of R's and S, any number of R's and S, any number of R's and S. And then at the very end, you might end with 0 or more R's, right? So that shows you they're the same. How about that? Did people get that answer?
Yes, sir.
All right, excellent. So here's a little machine. I guess it's actually in a DFA. And so I was asking, give me a regular expression to represent what it can represent. And you could just eyeball it, and maybe here's one answer, here's another answer, and you might be able to just eyeball it and write those things down. Or if you really wanted to, you could try to run that crazy algorithm I had. Remember the crazy algorithm says, what strings can get from A to B and then to C, right? Well, the strings are A followed by B star followed by C, right? So that's where we got A, B star, C are the strings that can go up here, A, B star, C, right? And then we can, so if we deleted that, if we rip this node out, the other way to get from this node to this node is to go directly across at E. So how do you get from this node to this node if you rip this out is this right here. Oh, no, not up to here. You say, well, there are two ways to get from here to here. Either I go up to rip, I do B star at rip and I come back down, or I go directly across, right? Does that make sense? And then you can ask, well, now how do I get back from here back again? Well, there's only one way to get back. I get back with this D. So if this regular expression here, from here to here, tells me all the ways I get from here back again, right? And what am I accepting? I'm accepting this node right here. So you can repeat that as many times as you want, right? Does that make sense?
Yes.
And here's a different answer. It's pretty much the same. We just brought the D to here and the D to here. And if you rip this node out first and then ripped out this node, you would get this answer. And if you rip this node and then rip this answer, you know that you get this answer. How did you guys do on this one?
So Professor, if it's if you do union empty string, will it still be accepted?
To where? The union
So
where?
if you do if you do it, so the right rejects, if you do it with so instead of the star, if you do union empty string or empty string.
You need these stars here because it could be infinitely long. I could go infinitely around this B. I could go infinitely around this loop. You definitely need two stars.
Oh, right. No, I mean like instead, not instead of it, like concatenating it. It's redundant, I guess. Oh yeah, never mind. It's redundant. I did.
Oh, yeah, you good?
Yeah, it's redundant. Yeah, I realized. Okay.
All right. How are you doing, Shanaz? Are you getting this?
Yes, we got this. Yeah.
Excellent. All right. So now here's a little machine. Here's a little machine. What does this accept? Well, it can accept, you go round and round and round anything, and then to accept, you have to end with the 0. So L1 is anything that ends with the 0. Now, if you star L1, then you can have, here's sort of a trick question, because you can do these guys, all right? This guy does L1 include the empty string? No, because it has to end in a 0, right? But if I repeat things from L1 some number of times, then it will be anything ending in a 0, right? So it still feels like anything ending in 0, but you have to note that the star could also be the empty string, right? So if I start it, if the star said I want 0 occurrences of L1, then I would get the empty string. Right? Do people get that? Now this one, what does it do? Well, it's copied direct out of the slides. You could have remembered it was there and looked it up. You see, as you get ones, you move forward around, so it's sort of counting forward mod 3, and the zeros come backwards, so it's counting backwards mod 3. So where am I sitting is the number of zeros minus the number of ones mod 3. And when do I accept? When here the sum is 0, and then one of these is 1 and one of them is 2. And so as long as you're not on that, then you're good. Right? Does that make sense? Right. And then how do you build a machine from it, right? we talked about it in class. You write the one machine out here, the other machine out here. That your new machine will have, it's sort of the, right, we have a row for every one of these states, a row. We have a column for every one of these states. So if I'm in this state, it tells me this machine's in that state and this machine's in that state, right? As I'm running this one, I'm kind of running both of them in parallel. I'm keeping track of where am I in this machine and where am I in this machine, right? And then you put an edge if a gnome will follow that, right? If a gnome is anywhere here, right? Then the gnome could do one of two things. If it gets a 0 or 1, it could just stay here, right? The gnome can always just stay here. And if the gnome's staying here, then it's following this path just like it followed this one, right? The gnome is doing this. But if it gets a 0, then this gnome could fly down here. So it's flying from this set down to this set. But when you get a 0 here, you come, right? If you're in this node, then you come back 1, right? So that's why this node is going back 1 to here. Does that make sense? Did you get that, guy? Maybe not.
We got the final, like the accepting state, but we did a lot of redundant transitions.
Right, right. So you didn't do it by my method of just doing the cross product.
Mm.
Right. Oh, I didn't tell you about accept states. All right. So what do we want? We want to say yes. This is intersection. So this is an and. When L1 is accepting and L2 is not accepting. So which one's L2, right? This guy here is L2. All right, so when is L1 accepting? L1 is accepting in this row, right? And when is L2 accepting? L2 accepting in these 2 columns, but we want L2 not to accept. So that's this guy. And so if we're here and we're here, then that's our only accept state. Right? Does that make sense? Any questions about this guy? So the danger of having some big complicated machine is that the TA might not know what's the right answer. Hopefully most people will just copy this out. All right, you got this question? Should we go on to the next question? All right, I kind of stated I really love this machine. And the reason I love this machine is, well, I invented it myself. That's one reason I love it. And the other reason I love it is that it's an NFA with basically 3 states, but the DFA requires 2 to the 3 states. So you can generalize it to you have n+1 states, right? That needs 2 to the n states to convert into a DFA. So it proves, in general, when you take an NFA and convert it to a DFA, the number of states can blow up exponentially because you have right? You keep track of every subset of where the gnomes might be. And all right, so I did give you I was going to give you some hints. And then I figured, so had this been a test you were writing in a classroom, I would have probably given you these hints. But given that you could look them up in the slides, I figured I wouldn't give you the hints. But this is just how do you do the conversion from an NFA to a DFA, right? You have the clones working on, you have a bunch of clones working in parallel, following all possible paths on the NFA. And I don't have any epsilon transitions, so that should make your life easier. And there'll be 1 DFA corresponding to every set of possible NFA states that contains a clone, right? And here's my other hint, which I think I said this hint during our tutorial, right? start with the DFA's start state, and then you keep repeating. What do you repeat? Is you figure out from some state, you choose some state of your DFA, you choose some character, you follow, you start in that state and you see where you get to. All right, so let's do that. Let's do that here. Let's come down. All right, this is my machine. And well, where does the machine, here's the start state is right here, right? So before, and we don't have any epsilon transitions. So when the gnome starts, we only have one gnome sitting right there, and he can't go anywhere until he gets a character. So where are the gnomes before we get any character? There's only one gnome, and he's on the star state. And so we're going to call that state the set that only contains star. And that's our star state. Everybody buy that? All right. So now suppose I have one gnome here and he reads a B. Well, he has to stay here. As long as he's reading a B, he has to stay here. Right? So that's why if he has one gnome on here, he gets a B, he just stays here. Right? But if we have one gnome that's here and he gets an A, he has a choice. He could stay here or he could go over to 1, right? And that's why we go from a gnome on star, you get an A, then we have a gnome on star, and we got a gnome on 1, right? Everybody buy that? Right? Now, suppose I have a gnome on 0 and I have a gnome on 1. Sorry, I keep calling it 0. A gnome on star and gnome on 1, right? And if I get a B, well, what always happens? The gnomes that are over here, right, always just move forward, right? These always just move forward. Any gnome that you have over here shifts along, right? So here, this 1, the gnome on 1 shifts over to 2. This gnome that's on 1 shifts on 2. These gnomes that are on 1 and 2, they shift over to 2 and 3, right? Gnome on 1 and 2 shift over to 2 and 3. Gnome on 2 shifts over to 3, right? But let's think about what the gnome on star does. First off, note there's always a gnome on star. And all of these sets have a gnome on star. And that's because the gnome that's on star can always just stay on star, right? And what can that gnome on star do? Well, if he gets a B, all he can do is stay there, right? So if this gnome on star, if he gets a B, he just stays on B. But if he's on star, if he gets an A, he can be on star and on 1, right? So this star moves to star and to 1, and when there's an A. And when there's a B, this star just moves to star. So similarly, this star, when there's an A, goes to star and 1. And this star, when there's a B, just goes to star not 1, right? This star here with an A goes to 0 star, and this star with the B goes to 0 not 1, right? And everybody else is shifting forward, right? The 1 shifts over to 2, and the 2 shifts over to 2. This 2 shifts over to 2, 3, and this 2 shifts over to 3, right? Does that make sense? Now, coming back now from these guys, it's a little trickier, right? If I have this, if I have a gnome on each place, then the gnome on 3, the gnome 3 dies, right? He has nowhere to go. So all of these 3s just die. And what happens to the gnome 1 and 2? They shift forward. So we can kind of think about the 3 not being there because the 3 doesn't count. So it's this, in some ways, this state is exactly the same as this state, right? These two, this one has a 3 in it, but this one doesn't have a 3 in it. But in terms of going forward, this A brings me here and B brings me here. So if I'm here, A keeps me here. And if I'm here, B takes me here. Right? Does that make sense? Right? Because if I'm here, this one, if I'm here, the 1, 2 moves forward to the 2, 3. Oh, to the two, if the 1, 2 moves forward to the 2, 3, which is the same as here and here, right? The 3 disappears, and the guy on 0 on star, if he gets an A, it turns into a 1, and if he gets a B, it turns into a 1 blank. Right? Does that make sense? And that's the same as these guys here. The 3 disappears. So what I did was I said, well, the 3 disappears. Here, the 1 moves forward into it. Right? So here, this is kind of like doing star 1, right? Star 1, A takes me here, B takes me here. And so that's the same as this guy. A takes me here, B takes me here. Anyway, it was kind of finicky. Were people able to get this?
Yes, sir, we got this.
Excellent.
Yeah, we got this.
Excellent. Was it finicky? How long did it take you to fill it out?
Long
1 hour.
time. Long time.
Fair enough. Fair enough. Did you find the pattern in it?
It was fun. It was the most the funniest question. Like,
Oh, good. I'm glad it was fun. All right. So now the next question is to label each string here, each state with 3 characters that will reach it, right? So here, BBB stays here. What about BAA? Well, BBA can make here. How about this string? BAA can make it here. This guy here, BAB can make it here. What can make it here? AAA. What can make it here? AAB, right? Each of them. And now you can ask, well, can any of them get 2 3-character strings? And the answer is no. Why? Because look at, I've used them all up, right? I hope you notice how many strings are there with 3 characters? There's 2, 4, 8. How many of them do I have? 1, 2, 3, 4, 5, 6, 7, 8, right? There are 8 3-character strings, and you use them all, right? So each of them, so this is a unique labeling of 3-character strings. All right. Now we ask the question, what's the language that this computes, right? So one language is, somebody pointed out here that I screwed up and I have ABA here twice. That was purely a typo, but maybe it should have been a hint that that wasn't what I intended. I guess what I intended is for these 4 strings, right? Because these, oh, I didn't tell you who the accept states are up here, right? These are the accept states, because you only accept if you have a gnome 3, right? So these guys all have a gnome 3, so you accept. And this set was supposed to have been these 3 strings, these 4 strings, and I clearly typed it wrong. All right. Now, what's this set of strings? It's the set of all strings who, if this is the last character, and this is the second last character, and then this is the third last character, it has to be an A. right? And that's what our language is this. The third last character has to be an A. And why is that? Because once you start moving, you have no choice, right? Your only choice is when the fairy godmother is going to push you forward, right? So here, what's she going to do? She's going to keep you here until you have 3 characters remaining, right? If there aren't 3 characters, then you can accept, right? If you have at least 3 characters, she's going to keep you here, you're having 3 characters left. And now we have 3 characters left. We do the third last character has to be an A, and then the second last character, and then the first last character, then the last character, and we get what we needed, right? Does that make sense? Do people follow that? Right? And the reason I gave this as the counter, right? It says that the third last character is an A. Is it's sort of hard to keep track of, do we read the characters left to right or right to left? But so I often get muddled between this and this, but there's their answer, right? Does that make sense? And so what does a DAFA have to
Oh,
remember?
Professor,
Yep.
I have a question. So
Yes.
for the previous question, you told us that we should select multiple choice, L0 or L1 or L2. So L0 also they also accept it? Because all
So, people ask, maybe this is a language issue. I grew up taking multiple choice questions, tests, right? And in my definition of a multiple choice question, there are multiple answers, but you can only give one of them.
So if we give L0, would that also be correct?
No, L2 is definitely wrong because L2, because
Oh, I meant
our language,
L0.
what?
L0, I meant.
Wrong, because it accepts, these might be the strings it accepts that are length 3, but it accepts strings that are much longer.
Oh,
Right?
sir, but that language is bounded, right?
Yeah.
L0 is bound. It only has 4 strings, so that should accept it, right?
Does this machine accept this string?
It can be of any length, so it
Be of any
can't
length.
just.
How do I accept the string? I go B, 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 B. I get the 4 B's, and then I do the A, and then I do the B and the B. Right? So
Oh, yes.
this machine accepts the string. Right? And it's the loops coming back too. What about this? How about this machine? Right? I go B, 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 4 B's, followed by an A, followed by a B, followed by a B, followed by a B, and I accept. Right? So this string is accepted by both of these machines. So the language that this machine accepts is not this language, right? It's this language. Right? But it's not worth, hopefully that didn't mess you up I don't think it would have messed you up in the future questions, because the future questions only focuses on strings of length 3. All right, well, maybe D, maybe you'll get D wrong. D says, what do you have to remember about the string? Right? And as characters are coming by, you don't know when the string's going to end, right? So you don't know whether the character you're reading now is the third last, because you don't know when the end's going to come. And when you get to the end, you have to remember the third last, right? So you're going to have to remember the last 3 characters. And if you go back up here, right? In fact, what's written in purple is, once you've gotten 3 characters, what's in purple is the last 3 characters, right? I'm only here if all I've gotten in B's. So the last 3 characters is B's. And then if I got an A, right? Then the last 3 characters are BBA. And then what happens when we get another character? This B shifts out, and we get that the last characters are BAA or BAB, right? It's remembering the last 3 characters. So suppose we have this. When we read a new character, this B shifts out. And what we're remembering is AAA or AAB, right? So right here, suppose the last 3 characters were ABA. Those are the last 3 characters you read. And you get another character. So what you're going to do is you're going to forget the A. You're going to forget that first A and remember the BA. The BA with an A gives you BAA. A BA with the B gives you BAB. Right? Does that make sense? Am I killing you guys? Am I killing you, Shanaz?
Yeah,
Makes sense, but
yeah, we got it partially right.
Partially got it. All right. All right, you following it now?
Yeah, now it makes sense.
Right. It's a hard one. I know it's a hard one. All right, so now let's see if people kind of right. So what did you have to remember? You kind of have to remember the last 3 characters. All right, so now we need to prove that no DFA can compute this with fewer states than the one you've constructed above. And how do you do that? You do that with the bumping lemma, right? So, so how do you do the bumping lemma? Is you let S be some set of strings. And what am I going to let my S be? It's going to be the set of all 3 character strings of A's and B's. And why is that? Well, you know, you needed 1 string to distinguish each state. We needed said, you know, the whole point is that every string in S needs to go to a different state. So here I have these different strings, and I want to prove that each of those strings needs to go to a different state, which is what I have here, right? Each of these strings goes to a different state. So what is this? This is the set of all strings of length 3 of A's and B's. Did people get that part? No, maybe not. All right. All right. So that's what my S is. And we'll have to show that each pair of them is distinguished by the language, right? So that tells me, if we do that, then the bumping lemma tells me that that any DFA computing L needs at least that many states, right? Which is how many states my DFA has, which completes the proof. People follow that bit?
So when you said this completes the proof, I mean, the rest of it is required as well, right? Where
Well,
we,
you're required as well. We will show, assuming we have showed that it completes the proof, right? And then now what we're going to do is show, right? All right, so how do we show? We have to show that every pair of them is distinguished, all right? So let alpha, to do that, right? Let alpha and beta be 2 different strings in our set, and we need to distinguish them. So how do we do that? I have 3 cases, and the cases depend on, we know alpha and beta are different strings. So they have at least 1 character that's different. And I'm going to have a case depending whether they differ in the first character the second character or the third character? All right, so in the first case, suppose they differ in the first character, right? And moreover, let's assume that alpha has the A and beta has the B, right? So what is my alpha? My alpha is some string of the form A something something, and beta is of something of the form beta something something, right? And I kind of gave that hint here, right? Now, I say that this alpha is in the language, right? It's in the language because the third last character is an A, right? And actually, the truth is, even if you had done that other language, even though I had a typo, maybe I should have made the effort to fix the typo, right? If I fix the typo, what that is, then right, if it starts with an A, then it's a yes. And if it doesn't start with an A, it's a no, right? So even if you'd gotten L0 is your answer, then you should have been able to got that, right? So here, this is a yes string, and this is a no string. So the language differentiates between them, right? I could have my zeta be the empty string, and these are differentiated, right? Does that make sense? All right, so now let this be alpha. Alpha is a 3-digit string with an A in the middle. Beta is a 3-digit string with a B in the middle. And I need to find some zeta, right? So I don't know whether this is a yes or this is a no, right? Because I don't know what this character is. So I need to shift them. I'd shift them by letting zeta be any string. I don't know, it's any string of length 1. It didn't matter what it was. It's a string of length 1. And when I shift, then what's alpha zeta? Well, I get the beta in the end, the B on the end, right? And now the third last character is an A, so it's a yes. Here's the third last character is a B, so it's a no. And then in this case, I shift it by 2. I have my zeta be too long. So here's the third last A, third last B. Did I kill everybody?
Yes, sir.
Yes,
But
yes.
this, yeah, with this question, yes.
Yeah, we got murdered.
Fair enough. Fair enough. But the good news is that probably everybody got murdered, in which case the distribution would be just fine. All right. People kind of understand this example now?
Yeah, I guess I remembered the bumping lemma when I thought about the question, so I got it, hopefully.
Right. So I don't know. Was it too hard? Would it have been better if I told you that the language was L1? I mean, that would have helped, I guess. But actually, I think you could have done, well, L2 is in the wrong direction. But anyway, should we go on to our grammar? Right. So now we need to come up with the context-free grammar of all strings of A's and B's of odd length. We need the first and the last character to be the same, and we need the middle character to also be that same character, right? So the first, middle, and the last are all A's, or the first, middle, and the last are all B's. So S is going to be our start non-terminal, and it will generate L, right? And then I'm going to have a new terminal, a new guy called non-terminal called T sub A. The A is just giving it a name, and it's going to be all strings of odd length where the middle character is an A, right? All we're going to require of this to generate it is that it has to be odd length and the middle has to be an A. And this is all strings of odd length where the middle character is a B, right? And what C is any character. It's either an A or a B, right? So then what is an S? How do you get an S, right? It has to be of odd length and the middle character has to be an A. Right? So, all right, so and the middle character has to be the same, right? So here, look at this string here. It starts with an A, it ends with an A, and it has an A in the middle, right? So these guys are all in our language. And what about this? Oh, that's just an A by itself. And the first character is an A, and the last character is an A, and there's an A in the middle. And this here, it starts with A, it starts with B, it has a B in the middle, and it ends with B. And same with this, right? All right, so everybody agree with that grammar? And then how did I get these? Well, all we need here is that it's of odd length. So this is an A, and it has an A in the middle, right? So that has an A in the middle. And then what's this? Well, it can be any character at all, followed by a string with A in the middle, followed by any character at all, right? So you take any string with an A in the middle, and you spew out some character in the front and some character at the end, you're gonna get a string with an A in the middle, right? Does that make sense? So it's gonna keep spewing out characters, and then it's gonna plop an A in the middle. And same with B. And what's a character? A character is either an A or it's a B. How's that? Did you guys get that?
Mostly. The only one I didn't account for was the single strings, just the A and just the B.
Right. Fair enough. How about you, Shanaz? Are we killing you?
Yeah, this is also, we probably got partial marks on this.
Good. Anybody else? Thoughts on it? All right. Now, what do we need? We need a string. Any string such that if you reverse it, you get something different than itself, right? It's not a palindrome. And you could have actually, as I said during the test, you could have actually ignored all of this because what you have to do is this. And what is this? Well, I guess what I'm saying is if the strings in the language X and X reverse are different, then it has to be different at some, it needs to be some index I and some index n, right? Here's I and here's n minus I, and they're different. So when you flip it, they're different in that spot, right? So here, this is any string of length I. It begins with the string of length I. It ends with the string of length I. And then the next character are different, right? And then you can have anything at all in the middle, right? And this is the same, except we replace the B and the A, right? So how do we get a grammar for it? Well, let S be this whole language. Let T be any binary string, any AB string at all. Let C be any character. All right. So what is S? Well, what we're doing is we're spewing out, right? How do you, what I told you to do is you link this and link this, right? Here, this I and this I are linked. So they have to be spewed out, right? And here, what are we doing? We're spewing them out, right? We're spewing out characters here and here, and then then what do is what do we plop in the middle? Well, what we plop in the middle is this thing, right? B followed by anything followed by an A, or we plop in this thing, A followed by anything followed by a B, right? So what are we plopping? We're plopping A, anything B. We're plopping B, anything A. Right? Does that make sense? And then how do you get anything? Well, you just spew out as many characters as you want. We have the empty string. Do people get this one?
Almost 95%, I guess.
Almost. And this is right here, we're spewing as well, right? If you have a string that's odd length with an A in the middle, right? What do you have to do? You can spew things on the outside and then plop the A in the middle, right? It's the same spewing, plopping. And that was the whole test.